So now we're going to look at the third case. The third case is where we actually have complex eigenvectors. So we're going to look at the third case of complex eigenvectors, complex eigenvalues. The eigenvectors are not complex. The eigenvalues are complex. So that means your lambda 1 would be alpha plus beta I, and it has different eigenvectors of k1 and k2. I'm sorry, k1 and the complement of k1. And that's what we do. We put this bar over top of it. That means we have a complement of k. So anytime you do that, so if you write any, like I could have written a complement here, put a bar over top of my lambda 1, and that would give me alpha minus beta I. We don't do that, but that just gives you an example of what we're looking at. And so we actually get these two eigenvectors from this one complex eigenvalue. And the solutions are that k1 e to the alpha lambda 1t plus and k2, k2 e, k1, the complement of k, e to the alpha 1t or lambda 1t. And so we end up with x1 is beta b1 cosine of beta t minus b2 sine of beta t e to the lambda t. And if you remember when we did complex back before when we were doing just a single equation, differential equation, we always had alpha plus beta I, and the alpha became the exponent in the e, and the beta became what was inside your sine and cosine. And what we had to figure out is what this b1 and b2 values, vectors are. And x2 is exactly the same, but it's the complement. This would be b2, actually not exactly the same. This b2 and b1 switch, and the sign switches. So you get these kind of different values. And what we had to figure out is what is this b1 and b2? And it turns out, and I'm not going to go through the theory of it, but it turns out b1 is the real part of that k1, and b2 is the imaginary part of the k1. So we're going to go ahead and go through an example of doing this, of how this actually works, and see what happens here. Sorry, I went way off in where I should have been. Okay, so we're going to go through this example. We're going to solve this differential equation, system of differential equation, -2, -3, 3, -2. So again, this is -2x minus 3y, 3x minus 2y, and you'd have the derivative of x with respect to t and the derivative of y with respect to t. So this is just written in this matrix form. And then we would again do this determinant of a minus lambda I, which is the determinant of this. So we're going to do the exact same thing. The process doesn't change just because you get different things. In fact, you don't know you're going to get complex conjugates or complex eigenvectors, complex eigenvalues, until you actually do this. And remember, this equals 0. So when I do this, I end up with -2 minus lambda times -2 minus lambda, minus a -3 times 3, which is -9, minus a -9, equals 0. And so when we end up multiplying all that out, we end up with that we've got lambda squared plus 4 lambda plus 13 equals 0. So when we multiply all this out and get all this, this is what we end up with. And then when I go to solve this, again, probably using my calculator, I would use the C-solve so you can get complex answers out of it. I end up with lambda is equal to -2 plus or minus 3i. All right, so now we have that. And so now we know we get complex eigenvectors, eigenvalues. Let's do that backwards. So we have a minus lambda I, again, that same process we're working with, times k1, and that's going to equal 0, just as before. So a minus lambda I is right here, so it's going to be -2 minus a -2 plus 3i, minus 3, 3, and -2 minus a -2 plus 3i. We actually only work with the positive one, when we do these, because they're already conjugates, they will actually work out okay for us. So we're just going to go ahead and do the -2 minus a -2 plus 3i, and then -3 and 3, and then we're going to have -2 minus -2 plus 3i. So because they're complex conjugates, you only need to work with the positive one. You'll get the exact same answers sort of in the end if you use the negative one, but we decided it's easier just to use the positive one. And then it's going to be times K1, K2. And that, of course, equals 0. So when we do this, we end up with, this is going to be -3i, then -3, then 3, and then -3i times K1, K2. So now what we end up with is we're going to multiply things together just like we always do. -3i times K1 minus 3 times K2, that equals 0. And 3K1 minus 3i K2, that also equals 0. So we end up going and solving this when K2 is equal to minus I times K1. This other one says the exact same thing. This one also says that K2 is equal to minus I times K1. So what we can do is we can again pick just like we've done before. There's really nothing new here. It's just we have complex numbers there. So what we're going to do is let's go ahead and pick something for K2, or sorry, K1, because we have K1, K2 in terms of K1. So maybe I could pick, I don't know, 1 for K1. And that works just fine. You could pick anything you want. You could pick 50 if you like the number 50. Just your numbers are going to get bigger. And then you end up with K2 is equal to -I. All right, so we end up with that. And we'll see where that goes and what happens with that. Okay, so now we have that. And we can now go, oh, well, let's go look at what the K is. So K1 is the vector 1, -I. And I just set up above in the previous page that your B1 is the real part of K1 and your B2 is the imaginary part. So I think we need another page here. So we'll go to another page. So B1, oops, let's go to a different color. So B1 is the real part of your K1. So that's what RE means, it's just a real part. So if I look at your K1, so let's write down the K1 again. K1 was 1 and then -I. Okay. So we have, this is my vector. The real part, 1 is real. In the I part, there is no real part. You can think of this as 1 plus 0i and 0 minus I. So your real parts are the 1 and 0. Your B2 is the imaginary parts of K1. So looking at it this way, because this is 0i, you have a 0 and a -1, the things that are in front of the i's. So the imaginary parts just are the coefficients of your i's. So now we know what B1 and B2 are. And so now we can get our x. Our x, if you remember correctly, was B1 times, we'll go ahead and do it as x1. So that was B1 times the cosine of beta t plus B2 times the sine of beta t times e to the alpha t. So that was your x1. And I actually have a slight mistake here. This is a minus. All right, so now we know what B1 is. B1 was 1, 0. Beta was, this was our eigenvalue was -2 plus 3i, so beta is 3. B2, we just found out to be 0, -1, sine of 3t. And alpha, this was -2 plus 3i, so it's -2t. So there's your x1. And we do the exact same thing to get x2. X2 is B2 cosine of beta t plus B1 sine of beta t e to the alpha t. So that means my x2 is going to be 0, -1 cosine of 3t plus 1, 0 sine of 3t e to the -2t. And then we can put this all together to get your x. X again is always c1 times x1 plus c2 times x2. So that would be c1 times 1, 0 cosine of 3t minus, I always get that negative sign wrong, minus 0, -1 sine of 3t times e to the -2t plus c2 times 0, -1 cosine of 3t plus 1, 0 sine of 3t e to the -2t. And that's what you do when you get complex roots, get complex eigenvalues.